Numerical integration definitely is a high-end topic in single variable calculus. You got here by going through differential calculus as well as integral calculus. You've solved a lot of problems very diligently, and because you've worked in this protected environment where exact answers are possible for the most part, I would think, in fact I would hope, that you have an intrinsic desire to just do a problem right, to get the answer and to get the correct answer. However, as we move towards situations in which an exact answer can only be obtained numerically, we need to step back from that a little bit to also see the philosophy of numerical integration and to not be too, let's just say, intimidated by the fact that beyond a certain realm, we really can't get an exact answer anymore. That is a transition that can be a challenge. It was a challenge for me, and I was a rather good student, mainly because you're starting to feel a little bit insecure when you can't get the exact answer anymore. Let's take a look at what numerical integration can do for us, and we'll start with a fictitious conversation that you and I might even have in the classroom. So, what do we have here? Let's start with a question. How do you compute the integral from negative 1/13 to 7 over 27 x squared dx? Well, in the realm from which we are coming right now, the answer is, well, I compute the antiderivative, which is 1/3 x cubed, and then I find f of 7 over 27 minus f of negative 1/13. And that's really tedious, but certainly thanks for being persistent, thanks for being hard-nosed. If your teacher wants you to do that by hand, it is not a bad thing to do. For my personal judgment, well, let's see, I would have to compute 13 cubed and 27 cubed. I know 13 squared is 169, and we both know that 27 squared is 729, right? You know that? So, yes, it can still be done, maybe even, and it wouldn't be a bad exercise to do it in your head, but certainly with paper and pencil, but it's just really, really tedious. And so the other answer, and sometimes you just do that because you want to prove a point, the other answer certainly would be that my computer will give me a number, and let's be perfectly honest, that's probably the answer that you get from me for something this ugly. There's another answer, which is I let my computer find the antiderivative, and you know I'm old school, so let me give you an old school answer before this one is even finished, and that is wash your mouth out with soap. The hard part in this problem is definitely not the antiderivative, and if you first compute the antiderivative and then let your computer plug in the numbers, then you might as well let the computer work the whole integral. If you're just interested in the number, there's no point in doing that intermediate step. Your computer has a definite integral function, you might as well use it. Okay, so let's ask that same question with a different function. How do you compute the integral from negative 1 to 1 e to negative x squared dx? Well, I try to compute the antiderivative, and I can't find the antiderivative. That's not good. So, and that's both of us. I can't find a decent antiderivative there either. So maybe my computer can find the antiderivative. I'm not going to go through that because, well, the computer can't do it either, unless the computer takes something like a sidestep, such as using the fundamental theorem of calculus in the derivative form or so. And it actually turns out that it can be proved that there is no closed formula for the antiderivative of e to the negative x squared. So that means finding the antiderivative and plugging in the bounds, that's out. But my computer will still give me a number for this thing, right? It will give me a number for the definite integral, and that's exactly the point of this presentation. The definite integral is a geometric construct. That is something that sometimes gets lost in this reflex, and it's not a bad reflex that we have developed, which is to find the antiderivative and then plug in the upper and lower bounds and subtract it. But technically, antiderivatives were just a tool to get to this geometric construction that uses Riemann sums and which we are going to generalize in various ways. So a definite integral can exist even, and usually does exist, even when there is no pretty antiderivative. And as should already be clear from number 2, it turns out that approximation is the only way to solve this integral up here. So what this presentation does is this presentation will show how integrals can be approximated numerically. And we certainly have these functions hardwired in computer algebra systems now, but it's good to know what happens behind the scenes, because it could happen that in a sophisticated application, even in industry, you may actually have to go into the code and just know what the machine does and maybe even tweak it a little bit. It's becoming less and less likely because the libraries and the canned codes that are out there are becoming more and more sophisticated, but as we have seen with a lot of this calculus, it's just good to know how this stuff works so that if something unexpected happens, you don't start floundering, you can try to track down what happened. Alright, so you could conclude this, and so it's well so because e to the negative x squared does not have an antiderivative, and don't even finish that sentence. That's wrong. Don't finish that sentence. The function f of x equals e to the negative x squared has an antiderivative. So even though I've just told you that we're not going to use antiderivatives, the antiderivative exists. And the antiderivative is capital F of x equals integral from 0 to x e to the negative t squared dt. That's not cheating. That's the derivative form of the fundamental theorem of calculus. That short presentation that we had, which, because we don't use this form so often in regular calculus, gets buried a little bit. But anytime you can't find an antiderivative, you can always use, if necessary, the derivative form of the fundamental theorem of calculus to write down a formal antiderivative. Now, if you can actually find a nice antiderivative, then you might not get too many points for that on a test. And so you want to be on top of your integration methods. But technically, you can always write it down. What you could then, of course, say is, well, how do you compute that antiderivative, Mr. Genius Teacher? And, well, you compute it numerically. And, thank you very much for your kind words. I appreciate that you think I'm the man, because I think so too, right? Okay, yeah, let's keep going here. So, let's actually get to it. And, this presentation is going to be long. There will be quite a few derivations, but those are given to just show you where the formulas come from. We are going to re-emphasize the geometric nature of the definite integral. What you'll typically need to be able to do also on a typical test, of course you again want to verify that with your teacher, but typically you need to be able to use the formulas. That's not going to be that bad. And you need to be able to do the error estimates, which we're going to do at the end, even though we'll only have 2 examples there. You want to look at those also very carefully, and then again check with your teacher if you have to have certain things memorized here. But overall, a lot of this presentation really is background to just get you into this idea that there are other ways to compute integrals than just the fundamental theorem of calculus in the antiderivative form. Alright, so technically, Riemann sums already approximate an integral numerically because we know the integral is the limit of the Riemann sums. So if we just use enough rectangles, we will get a good approximation. So why would you want to go beyond Riemann sums? Technically, they can be used to approximate to any level of accuracy. And so technically, we would not need to replace the definition with anything else to get approximations. So the hard problem to compute a definite integral really can be replaced with the simpler problem of computing a Riemann sum. But there are methods, such as the trapezoidal rule and the Simpson's rule, which can get the integral, the approximation faster. That means that it's with fewer computations, and we'll talk about what speed means a little bit later, and also then once we talk about the error bounds. So we can get that faster than approximation with Riemann sums with evaluation at left and right endpoints. Midpoint rule has some surprising properties that we're going to see, but midpoint rule technically is also just a Riemann sum. And so what we're going to do is we're going to replace our original approximations that use Riemann sums with left and right endpoint evaluations with faster ones. And so in order to go through the whole thing, we might as well talk about Riemann sums one more time first. So throughout this presentation, we will talk about an interval AB that is partitioned into n subintervals of equal length. And then, of course, the length of these subintervals will be denoted delta x, which is b minus a over n. And you know how that goes because that's exactly how we have introduced the integral. The endpoints of the kth subinterval will be xk minus 1 and xk, where xk is a plus k times b minus a over n. And the way that looks is that we've got our a, which is x0, we've got x1, which is one step to the right, so that's a plus 1 times delta x. x2 is a plus 2 times delta x. x3 is a plus 3 times delta x. x4 is a plus 4 times delta x. There's my magic dots, and then ultimately you've got xn minus 1, where you've got an n minus 1 here, and then xn is b, because when you plug in n here, you just get b, of course. So the interval is partitioned still in in subintervals of equal length. If you go deeper into numerical analysis, you could also see that people sometimes vary the lengths of these subintervals for a first exposure to numerical integration. That's a little bit much, so we're not going to mess with that. Okay, so let's first look at the stuff that we've already seen, and that's the left endpoint approximation, where if we want to compute the area underneath this function from a to b, well, we just take the left endpoint, put a rectangle over the first interval that has height being the value of the function at the left endpoint of the subinterval, and then we put another rectangle there, another rectangle, and another rectangle, and we do that up until we reach b. And we've got a last right endpoint here that we don't really use for anything, but that's the left endpoint approximation. And what was that? The left endpoint approximation from a to b of the integral of the function f within subintervals. And remember, that's really private notation here. That's not canonical. I'm not proposing that it become canonical, but it worked rather well for me as I wrote things up. The left endpoint approximation is just delta x times the sum of the values of the function at the left endpoints, which go from k equals 0 to n minus 1. Okay, let's look at an example. We want to use Riemann sums evaluated at the left endpoint with n equals 4 and with n equals 20 to obtain approximations of the integral from 0 to 1 minus x cubed dx. Now this is a toy problem in many ways, and let me face you as I'm telling you this, because we don't need numerical approximations to figure out the integral of 1 minus x cubed, right? We can compute that, we can get the exact answer. For the introduction of these methods, I want us to use a problem like that so we know what the exact answer is, so we can already see a little bit about what the quality of these various approximations is, so that we see that as we go to more sophisticated approximations, things get better. This is also a toy problem in the sense that we're using n equals 4, and you will probably have in your book some assignments that say use such and such a method with 4 rectangles or 4 trapezoids or 4 partitions to compute an integral. That's basically designed to just make you implement the formula by hand. That is not bad, but that's a toy problem because 4 rectangles, come on, that doesn't give us a terribly good approximation. And with n equals 20, that's then something where we're saying, okay, now program it. We're not going to do that by hand because that's cruel and unusual punishment. But that can show us how to put things into a computer. But overall, this is a training problem. What you would have in quote-unquote reality, and what we're also going to see when we talk about the error bounds, is that you have a function of which you don't know the antiderivative, and you are supposed to find an approximation of a certain quality. And we will see that in the error bounds. Okay, we ride. What is this here? This is what the function looks like, and this is the area we're interested in, which means that the area is the integral from 0 to 1 minus x cubed dx, which is, of course, x minus a quarter x to the 4th from 0 to 1, and that's 1 minus 1/4 minus 0, so that's 3/4. And so for this example, which occupies really most of the presentation because the derivations are rather lengthy, keep in mind that the answer is 3/4. 1/4, 2/4, 3/4. Well, you already know I've got a strange sense of humor, but the answer is 3/4. All right, so if we do this with n equals 4, we get an approximation that looks like this geometrically, and that would be an overestimate. And we also know that if we do this with n equals 20, we would have geometrically something like this, and we still get an overestimate, but the overestimate is a little bit smaller than what we had previously. Okay, good. Well, let's see how the computation goes. With n equals 4, what do we have? We have delta x is b minus a over n, which is 1 minus 0 over 4, which is 1/4. That means x0 is 0, x1 is 1/4, x2 is 1/2, x3 is 3/4, and x4 is 1, right? You can just count that through, and the interval could be uglier, the step length could be uglier, but it's nothing that's difficult in principle. That means that the left endpoint approximation from 0 to 1 of the interval of 1 minus x cubed with 4 intervals will be 1/4 times the value at 1, which is, well, 1 minus 0, so that's 1. Then you get 1 minus 1/4 cubed. 1/4 cubed, 4 cubed is 4 times 4 is 16, times 4 is 64, so you subtract 1/64, you get 63/64. 3/4, well, wait, 1/2. 1/2 cubed is 1/8, so 1 minus 1/8 is 7/8. And 3/4 cubed, that's where it gets ugly, right? So that would be 3 cubed is 27, so you get 64 over 64 minus 27 over 64, and 64 minus 27 is 37. So these computations, technically, you can still do them in your head or with paper and pencil, and that's not a bad exercise to do just to enforce number sense and computational ability. Well, now we need to add that up. And so what do we see? Well, 1 is 64 over 64, 63 over 64 is the same. 7 times 8 is 56, and this is already a 37 over 64. So what does that add up to be? Let's see, what's an easy target here? 63 plus 37 is 100. 156, 160, 220 over 64 times 1/4, which is 220 over 256, which is 110 over 128, which is 55 over 64. 55 over 64, great. That is 0.859375, and that's not an approximation because that's as many digits as this thing has. And we can see that the approximation is not that good because the actual answer is 0.75. Alright, so if we go to n equals 20 rectangles, we're expecting a better approximation, and of course we'll use a computer for that. So delta x is b minus a over n is 1 minus 0 over 20, which is 1/20th. xk is a plus k times delta x, which is 0 plus k times 1/20th, so k over 20. We set up the sum, which is delta x times the sum of the f of xk, which is 1/20th, sum k equals 0 to n minus 1, 19, 1 minus k over 20 cubed, like that. And if we stick that in a computer, again, I can still find, or the computer can still find, I wouldn't want to find the exact answer here, but it's 1239 over 1600, which is 0.774375, and so we can see that's a good bit closer to the actual answer, and that's of course what we want in numerical approximations. We want that as we increase our effort, we get a better answer. Alright, that's this one. Well, if we do right endpoint approximation, not much changes, right? The right endpoint approximation wants to approximate the area under the function from a to b, but this time we use rectangles where the height is the value at the right endpoint. We've seen all that with the Riemann sums, and so the summation then is basically the same, only now we're using the right endpoints, which means the sum goes from 1 to n. Okay, we're going to step through the right endpoint approximation a bit faster, so we do the same thing. Evaluate at right endpoints with n equals 4 and n equals 20 to obtain approximations for the integral. So here's what that looks like with 4 rectangles. It's an underestimate. Here's what it looks like with 20 rectangles. Still an underestimate, but probably getting closer. And so for n equals 4, we have the same delta x, 1/4. We have the same points x0 through x4. And now for the right endpoint approximation, we've got 1/4. And this time we start with x1. So we already had the 63 over 64. We had the 7 over 8 at 1/2. We had the 37 over 64 at here. And at the right endpoint at 1, we get 1 minus 1, which is 0, which means if we add that up, it's actually a little bit easier to compute because we just have the 63, the 56, and the 37. Well, 63 plus 37 is 100. 156 over 256, that would be 78 over 128, which would be 39 over 64. All right, I got that right. So you can see mental arithmetic, it's still fun to do, but ultimately, to determine how good the approximation is, we get a decimal. And again, it's quite a ways off from the 0.75 that the actual answer is. And if we do this with n equals 20, of course, we're using a computer. Delta x is still 1/20th. xk's are still the k over 20. Of course, if you do this problem cold, you'd have to go through these computations again. That's why I'm going to represent those things every time we do the computation. Right endpoint evaluation, then this time, it's the sum going from 1 to n, which means we have 1/20th, sum k equals 1 to 20, 1 minus k over 20 cubed, Same thing as before, only that the sum runs differently. That's 1159 over 1600, which is 0.724375. Okay, so again, it's closer to the actual answer. Now, the goal is ultimately to reduce the number n of evaluations that are needed to get an answer of a certain quality, or to get more accuracy with the same number of evaluations. So sort of keep in mind, or download the slides and open them up in a separate window. Keep in mind that we were about 0.1, 0.15 off with the left and right endpoint evaluations when we worked with n equals 4, and that we were still something like 0.03 off when we worked with 20 evaluations. Okay, so the thing here is the evaluations of the function take computational time. And with Riemann sums actually being pretty simple, really the bulk of the time evaluating the sums is spent evaluating the functions. So if we could cut the number of evaluations that we need to get a certain accuracy in half, then we basically cut the computation time in half. And that is huge even with large computers, because if you can cut computation time in half without putting more demands on your equipment, you certainly want to do that, because otherwise somebody will ultimately realize you're wasting my computation time, you're wasting money technically. Okay, so that would be huge. Even 10% in fact would be significant. And so the first idea to cut down on effort is to evaluate at the midpoint. Here's where we're technically looking a little bit into the abstract definition of the integral, which was that those Riemann sums could be evaluated at any point inside that interval, right? And so if we evaluate at the midpoint, well, the picture is still the same. We want to have the integral from, okay, this time around, I'm just going to show you a representative interval from xk minus 1 to xk, because we need to get a formula here first. Well, the midpoint is called xk bar, will be called xk bar throughout. And so that would be here, and so then the value would be f of xk bar, and our rectangle would be something that typically, for a typical subinterval, there would be a little bit sticking out, so a little overshoot, but it's paired with a little undershoot, and hopefully those will cancel so that we get closer to the actual answer than we would get otherwise. So the definition is, for the midpoint rule, you take a function that is integrable over ab, let n be a positive integer. You define xk bar to be xk plus xk minus 1 over 2, which is the midpoint of the kth interval. And then the midpoint approximation of the interval is given by midpoint approximation from a to b of f with n evaluations, or with n subintervals. And it's just delta x times the sum k equals 1 to n, evaluating the function at xk bar. So of course we also have to compute the xk bars, but that is typically a whole lot faster than evaluating the function at f. And you note that independent of whether we use left endpoints, right endpoints, or midpoint endpoints, we're always evaluating the function n times. So that's delta x times, if you want to write it out like this, also it's just delta x times f of the function at the first midpoint, function at the second midpoint, and so on all the way through. Okay, so we go back to our example. We want to use the midpoint rule now with 4 rectangles and with 20 rectangles to approximate the integral 1 minus x cubed dx from 0 to 1. Okay, so what would that look like? Well, here would be 4 rectangles that are worked out with midpoints, and we can see, I mean, it's not a definite overshoot or undershoot. If I had to estimate that, I would say it's maybe a slight overshoot. But we can also see that there are some cancellations here, and that's kind of nice, because that may help us get rid of some errors. And again, we also see that if we do this with 20 rectangles, well, we get a better approximation. Good. Okay, so now let's do the computations. Well, same story. First, n equals 4. Delta x is b minus a over n, which is 1 minus 0 over 4, which is 1/4. x0 is 0, x1 is 1/4, x2 is 1/2, x3 is 3/4, x4 is 1. And that means that x1 bar, the midpoint here, is 1/8. The midpoint of those is 3/8. The midpoint of these two is 5/8. And the midpoint here is 7/8. So yeah, you have to work with your fractions a little bit more. But, I mean, working with fractions up to a certain point is good for the soul. So then the midpoint approximation from 0 to 1 of the integral of 1 minus x cubed with 4 rectangles is 1/4 times the value of the function at all those midpoints. Oh, goodness gracious. Let's see if we can at least try to talk our way through that. And I didn't even work on simplifying denominators and all that, because apparently it's not even possible. Well, 8 times 8 is 64, and if you multiply that with 8, you come out with 512, because 64 times 8 is 480 plus 32, which is the 512 here. And so then 1 minus 1 over 512 is 511 over 512. 3 cubed is 27, right? So 512 minus 27, that would be 505 and then 485 in the numerator, because you've got 512 over 512 minus 27 over 512. Here we would get as a cube 125 over 512, and then 512 over 512 minus 125 over 512. Well, 512 goes back to 412, 407, and then minus 20 would be 387. And, oh goodness gracious, 7 cubed. Oh my god, who makes these problems up? I mean, yeah, it was me. Okay, so 7 squared is 49, 7 cubed would be 343, and 512 minus 343. 512 minus 343. That looks a little bit too large here. Let me think for a minute. And we're back. Yeah, I was off by 100. 512 minus 343 would be 212, 209, and then 169. So that's up here. And if you add that up, well, let's see, how would I add that up? This would be 500, 900, 996, 996, 1200, and so on and so on. Hey, I mean, that's it. Use a calculator. Why not? And so you end up with 1/4 times 1552 over 512, which ends up being 97 over 128. Let's be honest here. The point of this isn't mental arithmetic. If you can do it, or if you want to do it, it's a really good concentration exercise, but I don't want to waste your time here much more. And so ultimately what we get here, 97 over 128, that's 0.7578125, and if you remember the numbers that we had previously, or at least remember a general impression, this is a whole lot closer than the other approximations, and that's great. If we use n equals 20, then of course we ought to get even closer, and so delta x is, as before, 1/20th. xk are the same xk's as before, it's k over 20. xk bar, well, that's the midpoint between xk minus 1 and xk, so that would be 1/2 a plus k minus 1 delta x, which is the xk minus 1 here, and a plus k delta x, which is the xk. And well, 1/2 times 2a is a, and then k minus 1 plus k is 2k minus 1, and then we still have to divide by 2 there. So we end up with a plus 2k minus 1 over 2 delta x's are xk's. And so that would be 0 plus 2k minus 1 over 2 times 1/20th, so that's 2k minus 1 over 40. And so the midpoint evaluation, therefore, is sum delta xk equals 1 to 20 f of xk bar, which is 1/20th sum k equals 1 to 20, 1 minus 2k minus 1 over 40 cubed. So even though the number that we're plugging in now is a bit more complicated, it's still the same story here, right? So now if we evaluate that, and it ends up being 2,401 over 3,200, and we're not going to simplify that fraction. Don't think it can be, but what you realize is 24 over 32 is about 3/4, and so in fact the answer is very close to 3/4 here. So just by going to evaluating at the midpoint, we already have gained a lot more accuracy. All right, now the geometric thing now is that we're not limited to rectangles. The integral of a function is, or at least can always be canonically interpreted as the area under the graph. So Riemann sums are useful for the development of the abstract definition and the theory, because those give us reasonably simple formulas, but we can use other shapes to approximate the area. And so trapezoids are one of the first shapes that come to mind, because what we could do there is we could look at our function on a subinterval xk minus 1 to xk, and we could simply approximate the area under the function with a trapezoid. Well, then we have to figure out what the area of a trapezoid is, and hopefully working it out in such a way that we are only evaluating at the left and at the right endpoint, so that we only need to have f of xk minus 1 and f of xk there. And how does that go? Well, if you take this trapezoid and rotate it around the middle, you get two copies of that trapezoid, and well, the height of that combined trapezoid would be f of xk minus 1 plus f of xk, and so the area of twice this thing would be delta x times f of xk plus f of xk minus 1, and since we want to use only half of double of that, we would have f of xk minus 1 plus f of xk minus 1 plus f of xk divided by 2 as the area of our kth trapezoid here. Alternatively, look up the formula for the area of a trapezoid, and it is basically, as long as it's set up like this, it is 1/2 base times the sum of the heights at the left and right endpoint. You could also work that out by computing this as the sum of a rectangle and a triangle. So there are various methods to do that, and this is what the area under the kth trapezoid would be. So that's delta x over 2 times f of xk plus f of xk minus 1. And if we now add that up, right, because we would use k trapezoids, we would have that the total area is the sum of the ak, which is the sum of the delta x over 2 f of xk plus f of xk minus 1. Well, we can take the delta x over 2 out because it doesn't depend on k, and then we've got a sum of the f of xk's and a sum of the f of xk minus 1's. Well, we can change that. The sum of the f of xk stays the same, but if I sum from 1 to n over xk minus 1's, that's the same as if I start at 0 and go to n minus 1 with f of xk's. And so basically that would mean that the 0th value comes out, the nth value comes out, and everything else is doubled. So we end up with delta x over 2 f of x0 plus f of xn plus 2 times the sum k equals 1 to n minus 1 f of xk. Now, even though that looks more complicated, we're still just evaluating at those endpoints. We're still having, well, this time n plus 1 evaluations. For sake of fairness, of course, we use one more evaluation than with the Riemann sums, but because n is typically going to be large, the difference between n and n plus 1 evaluations typically is not significant. So this would still be a fair comparison in this formula. Now, the definition of the trapezoidal rule is that if you've got a function that is integral over the interval a, b, and n is a positive integer, then the trapezoidal approximation of the integral with n partitions is trapezoidal approximation from a to b of f with n partitions is delta x over 2 f of x0 plus f of xn plus 2 times the sum of the f of xk from 1 to n minus 1, which would, if you want to write it out like this, delta x over 2, value at the left endpoint plus value at the right endpoint overall, plus 2 times the value of the function at all the points that are intermediate to our partition. And as an example, we go back to our function that we have already played with, 1 minus x cubed. We use 4 rectangles, 4 trapezoids and 20 trapezoids. And so what would that be? Well, with 4 trapezoids, it looks like we're getting a pretty good approximation. And with 20 trapezoids, there's almost no difference between this blue area and the area under the red function. So it's all looking very, very promising, certainly. And so the computation with 4, we work out by hand. Delta x is still 1/4. x0 is 0, x1 is 1/4, x2 is 1/2, x3 is 3/4, and x4 is 1 as before. So the trapezoidal approximation from 0 to 1 of the integral 1 minus x cubed with 4 partitions is 1/2, right, because it's delta x times 1/2. So 1/2 times 1/4, which is a delta x, times value at the left endpoint 1, we had that already, plus 2 times the value at the next point, which was those 63 over 64, plus 2 times the next value, which was 7/8, plus 2 times 37 over 64, which was the value at x3, and then plus 0 just by itself, because that's the value at b. And if we add that up, well, we've done enough mental arithmetic for a while. I think we'll just, yeah, okay, we find a common denominator here. Okay, this is 1/8. 1 is 32 over 32. 2 over 64 is 32, so we just keep the 63. 14 over 8, we have to multiply that with another 4, and 14 times 4 is 56, right? Okay, because 8 times 4 is 32, so we expand with 4. And 2 over 64 gives us 32, so we keep a 37 here. So those computations are still possible again. 63 plus 37 is 100, 156, 158, 188. So this would be 188 over 8 times 32, which is 256. And if you simplify that, what do you get? You get 94 over 128. You get 47 over 64, I think. Yep, all right. So I'm back on my game here. Again, if you want to work that with a calculator, that's fine. The exact answer is 0.734375, which is an undershoot. That is not surprising because the picture looked like that. What is a little bit surprising, and we're going to come back to that when we're talking about the error bounds, is that the trapezoidal rule, which looks geometrically more sophisticated, actually doesn't give as good an approximation as the midpoint rule, because the number we got in the midpoint rule had a 0.75 and then some. So it was definitely closer to the exact answer than this one here. With n equals 20, well, delta x is still 1/20th. The xk's are still k over 20. The trapezoidal approximation from 0 to 1 of 1 minus x cubed with 20 partitions is delta x over 2 f of x0 plus 2 times the sum of the f of xk's from 1 to n minus 1 plus f of xn. And that's 1/40th plus 1, which is the value at the left endpoint, plus 2 times sum k equals 1 to 19, which is n minus 1. Function is 1 minus x cubed, so 1 minus k over 20 cubed, plus value at b is 0. And if you work that out, you get 1199 over 1600, which is 0.749375, which is again an undershoot. And, well, this is not so easily seen, but this is also not as close as what we got with the midpoint rule and 20 rectangles. So there's something going on here. All right, now it gets really interesting, and it becomes a whole lot more precise when we realize that we are not limited to straight boundaries, and that is Simpson's rule. And what Simpson's rule does is, again, it talks about the integral of a function is the area under the graph, and if we can approximate the graph with a simpler curve, then the integral of the simpler curve should be close to the integral of the original function. But keep in mind, we're not limited to straight lines. And so polynomials are often used in approximations, and Simpson's rule is a good example for that, because in Simpson's rule, we approximate with parabolas instead of straight lines. So Simpson's rule takes our kth subinterval here from, well, got a little bit too far, apparently I didn't have the xk's here. So what Simpson's rule does is it takes this and approximates with something that has straight vertical boundaries and then a quadratic top boundary. Okay, for a quadratic, however, you need 1 point, 2 points. You always need 3 points to determine a parabola. And you will need evaluations at f of xk minus 1, f of xk minus 2, f of xk minus 1, and f of xk right here. And so basically what we do with Simpson's rule, we want to stay with evaluations only at x1 through xn, or x0 through xn actually. And we're back. Okay, so evaluations at x0 through xn, which guarantees that the comparison between the methods is fair, right? If I start doubling the number of evaluations because I need that midpoint for Simpson's rule, then all of a sudden Simpson's rule would use more effort, and then it would only be right that should give a better estimate. So we must pair the intervals here. So for Simpson's rule, n must be even, which is one of the reasons also why in the earlier examples we used an even number of evaluations. Derivation of Simpson's rule is a bit hairy, so this is definitely background information. If you want to just scroll through that quickly, that's fine. Otherwise, just kick back and see what we can do. Take a generic parabola, ax squared plus bx plus c, on an interval from negative d to d. If I want to integrate that, well, of course, I can do that. That's 1/3 ax cubed plus 1/2 bx squared plus cx from negative d to d. And when I evaluate that, I realize that the quadratic term is going to go away in the subtraction, and the other ones are going to double, so I end up with 2/3 ad cubed plus 2cd. And if the parabola goes through the points negative d, y value at negative d, 0, y value at 0, and d, y value at d, then we also have that the y value at negative d is ad squared minus bd plus c. The y value at 0 is c. The y value at d is ad squared plus bd plus c. And if we add that up, we end up with y negative d plus yd is 2ad squared plus 2c. So that's already pretty darn close here, right? That's pretty darn close to this area. So if I now take y negative d plus 4y0 plus yd, I end up with 2ad squared plus 6c, right? Because that's the 6c. And if I take this thing and multiply it by d and divide by 3, and I can do that if I also multiply by d 3 over d. Well, okay, so this is multiplied with 3 over d times d over 3. And if I multiply this one with d over 3, I get the 2/3 ad d cubed. And if I multiply this one with d over 3, I get 2cd. I end up with this being the area, right? Okay, so this is 3 over d times the area under the curve. How do people come up with that? Well, this is just something where somebody wants to relate area to evaluations, right? So this is not something that I would expect the typical first-year calculus student to just come up with automatically. This is the kind of stuff that the professionals do, but the idea in numerical approximation of integrals was to relate areas to evaluation of the function, and we have done that here, right? So what would that mean? On the interval from negative d to d, the area under the parabola that goes through those 3 points is the integral, which is 2/3 ad cubed plus 2cd, which is d/3 2ad squared plus 6c, if we want to write it slightly differently. And that is d/3 y negative d plus 4y0 plus yd. And so for a parabola that goes through the points x2m minus 1, f of x2m minus 1, x2m minus 2, f of x2m minus 2, f of x2m minus 1, f of x2m minus 1, and x2m, f of x2m. So if it goes through 3 consecutive points in our partition, we have that the mth area here would be this integral, which ends up being delta x over 3. And that is because the d, well, yes, the d was exactly 1 delta x because we are stepping through the interval from x2m minus 2 to x2m minus 1 to x2m. So d really was delta x divided by 3 f of x2m minus 2 for f of x2m minus 1 plus f of x2m. Basically what we've done here is we have taken this formula and shifted it horizontally, realizing that the left endpoint evaluation is the value at x2m minus 2, the one in the middle is the value at x2m minus 1, the one on the right is the value at x2m. And so now if we want to have the total area, we would have to sum up all these areas, and we would go with m equals 1 to n over 2, right, because we've paired the intervals, so this n over 2 multiplied by 2 really hits all the points that we've been working with. So that's the sum m equals 1 to n over 2 delta x over 3, all these numbers, and we can see here that that adds up in a certain way, because the first one is delta x over 3 evaluated at x1, 4 times evaluated at x2, and once at 4 times at x1, and once at x2 plus delta x over 3, once evaluated at x2, 4 times at x3, once at x4, and so on and so on. And so we can see here that x0 we evaluate at x0 and multiply by 1, at x1 we evaluate multiplied by 4, at x2 we evaluate and multiply by 2 because we have that one twice. F of x3 is multiplied by 4, f of x4 is multiplied by 2 because we've got that one twice. F of x5 is multiplied by 4, f of x6, because we'll also have it in the next one, is multiplied by 2, and so on and so on. This one will be multiplied by 2, this one by 4, and this one is by itself. So the odd-numbered indices, the evaluations are multiplied by 4. Even-numbered indices, the evaluations are multiplied by 2. And the first one and the last one are just left by themselves. So the formula actually is delta x over 3, f of x0 right here, plus f of xn right here, plus the even-numbered indices, because they're always paired up. They're the last in one summation evaluation and the first one in the next one. And 4 times the evaluation at the odd-numbered intervals, because those are the one in the middle that gets the 4, that get the 4 from the formula here. And so that's Simpson's rule. Take a function that is integral over the interval with n being a positive integer. The Simpson's approximation of the interval with n partitions is Simpson approximation from a to b of f, of the interval of f, integral of f with n partitions. delta x over 3, evaluate at the first, evaluate at the 0th point, evaluate at the first, multiply by 4, evaluate at the next one, multiply by 2, evaluate at the next one, multiply by 4. That keeps alternating until at the end you've got that the second to last one is multiplied by 4, the value at the second to last one is multiplied by 4, and you add to it the value at the last point. And so that's delta x over 3, f of x0 plus f of xn plus 2 times the sum of the values at the even-numbered partition points, and 4 times the sum of the values of the function at the odd-numbered partition points. That's a mouthful, but certainly people would also want to know, where does this formula come from? And we've just seen it just shakes out that way in the derivation. Alright, so let's take a look at our function. Again, n equals 4, n equals 20, and the function is 1 minus x cubed. Alright, setup is the same thing, right? Delta x is still 1/4. The x0 is still 0, x1 is 1/4, and so on, just as before. Same story, same setup. The Simpson approximation from 0 to 1 of the integral of 1 minus x cubed with 4 partitions is now 1/3 times delta x, which is 1/4, times evaluate at the left endpoint, which is 1, plus 4 times evaluation at the next one, which was the 63 over 64, plus 2 times evaluation at the next one, which was 7/8, plus 4 times evaluation at the next one, 37 over 64, plus just the value at the right endpoint, which is 0. And again, you can piece that together. We get 1/12 here. Common denominator apparently is 16, so 1 is 16 over 16, 4 over 64 is 16, so we keep the 64. 2 times 7 is 14, times 2 is 28, and so this thing is 28 over 16, good. 4 over 64 is 1/16, so we keep the 37. 0 is 0 over 16, and then we add that up, and we get 63 plus 37 is 100, 128, 138, 144, so we get 144 over, 16 times 10 is 160, plus 32 gives us 192, and the cool thing here is that ends up being 3/4, right? That's amazing. Quick warning right away. In general, Simpson's rule does not give the exact answer. Simpson's rule only gives an approximation. What I did here is I wanted to have something where we could technically even still push ourselves through the computation and where we could get a nicely and easily remembered answer, which is why for this thing it actually accidentally works out nicely. Overall, that's not going to happen all the time. However, then we should expect that when we go with n equals 20, where the delta x is still 1/20th, when we go with the xk still being k over 20, when we set up the summation, where we really need the summation formula, right? Delta x times all this stuff, which ends up being, well, delta x is 1/20th, so we get 1/60th, value at the left endpoint 1, or value at a 1, plus 2 times the sum k equals 1 to 9, because n halves is 10 minus 1 is 9. Function at x2k, which is 2k over 20, and I didn't even simplify that here, right? Plus 4 times sum k equals 1 to n over 2, 4 times sum k equals 1 to 10, 1 minus 2k minus 1 over 20 quantity cubed, so that's the odd-numbered x's, plus the value at b, which is 0. You work that out, and that ends up being 3/4 also, and of course that's something that my computer just gave me. Again, remember, in general, Simpson's rule only gives an approximation, not the exact answer. But what we have a certain indication here, which is that the trapezoidal rule apparently works better than Riemann sums at the left and right endpoint. The midpoint rule apparently works better than the trapezoidal rule. And Simpson's rule apparently works much better than any of these rules. And so now the challenge that we have is to decide which method actually is the best of these methods. And in order to do that, we're going to race them. We're going to approximate the integral from -2 to 2, 1 over square root 2 e to the negative x squared over 2, which is an integral that is important in statistics, and we're going to ultimately also do a computation of this interval that doesn't use any prior knowledge of what the integral may be. But let's just go ahead and race those, and let me show you what we have here. The approximation is going to run fairly fast. So here's the midpoint rule, right? It takes our function, and it approximates with rectangles where we evaluate at the midpoint. Here's the trapezoidal rule. it approximates the area under our function with these trapezoids in blue. Great. So here's our n. N will go in steps of 2 because we need an even number of partitions there, an even number of intervals. Here's what the midpoint rule gives us as an answer. Here's what the actual integral is, or at least an approximation of that integral. Here's what the trapezoidal rule gives us. Here's what the integral ought to be. Okay, there should be one more digit here. The sums give us more digits, and I think I truncated everything else to 3 digits. Here's the error. That's just the difference between the sum and the actual value. Here is the error for the trapezoidal rule. That just is the difference between the sum and the actual value, rounded to 3 digits. Here's the percentage error, which tells us a little bit more because this one will ultimately get really small. And Simpson's rule uses these quadratic approximations that are really so accurate that I didn't even create an animation, because I think after the first or second step here, we wouldn't have been able to tell the difference between the areas anymore. And because that animation is rather challenging to write, I took the easy way out there. Well, what do we know? I've got the Simpson's rule here, and well, at least for the first one, the Simpson error is pretty darn bad. Well, that's probably not too bad, because when we just look at 2 rectangles or in 2 sum intervals, we're trying to approximate with a parabola here somehow, and that's of course going to give us a horrible overshoot. So at least on the first one, the error with Simpson's rule is actually pretty darn bad. We're going to see that as we increase. Well, look at n equals 4. I want to get 4. Can't get it. Ha, here it is. N equals 4. So now we've got 4 rectangles, 4 trapezoids. We get a better error. We can see that the midpoint rule error is about half the error in the trapezoidal rule. The error in Simpson's rule, look at that. The error in Simpson's rule is already beating the midpoint rule. We go with 6 rectangles or 6 partitions. Error in the midpoint rule is about half the error in the trapezoidal rule. The error in Simpson's rule is already 0.000. That's already only 10% of the error in the midpoint rule, right? And now you keep running that. Let's stop it right here at n equals 14. Simpson's rule has just an amazing error. The percentage error is way below 1%. Okay, the midpoint rule percentage error is also a good bit under 1%, but not at that much. And the trapezoidal rule, again, is lagging behind a bit here. And so if you keep going here, you can see geometrically, these both look like they're good approximations. At first, of course, because it's kind of weird that this one doesn't hit the area exactly. It feels kind of strange that the midpoint rule gives us still a better percentage error than the other one because of rounding. The absolute error is already rounded to 0. Simpson's rule, because I've displayed more digits, right? This is rounded to 3 digits. We're looking at the percentage error. Simpson's rule still has a much better percentage error and retains that all the way through, because ultimately, I think at the last evaluation that we've got, which is something like 62 or 64, well, maybe a little bit longer even, 72, yeah, okay, keep scrolling, 78, 80. I'm just going to run this all the way to the end here. 82 rectangles. The percentage error for the midpoint rule is 0.002, so it's still visible, at least as a percentage here with 3 digits. Trapezoidal rule percentage error is 0.004. Simpson's rule percentage error is just, I mean, that, okay, it's still there. It's 0.0000007. If you can get your hand on measurements and approximations that have a percentage error that is so small, that's basically an exact answer. I mean, those are already very close to exact answers, but you can see that Simpson's rule, as long as we keep it fair and keep the same number of evaluations, Simpson's rule is a lot more accurate than the other ones. And so the question now is, how can we figure out which method is best without knowing the answer already, right? And that's, again, I mean, look at me. Up to now, these were toy problems. Up to now, we had an oracle. Well, first of all, I mean, for the first one, of course, we had the fundamental theorem of calculus. For this race that I've just shown you, we had the computer used as an oracle, but somebody already told us what the answer is. Look, if you know what the answer is, you don't do numerical analysis. If you know what the answer is, you write down the exact answer, you move on. There is no point in doing numerical analysis when you already know the result, right? You don't need to do it. The real life situation is that you don't know what the integral is, and you somehow, if you're a numerical analyst, have to create a method that gives you an answer that is guaranteed to be within a certain distance of the actual answer. And that's what we're doing here with the error bounds. There are two ways to estimate error bounds, and only the last example really is the full generalized glory of what happens in numerical analysis, and the one in the middle just shows us how to use the formulas. So let's take a look at that. Basically, first of all, I just want to have consistent notation. The error, and I'm gonna call it nu sub n, that is encountered when approximating the integral from a to b f of x dx with a numerical result, numerical approximation from a to b of the integral of f with n subintervals. I will denote that nu n being numerical result minus the actual integral absolute value. This notation is not canonical at all. This is just, again, it's just like the other ones that I had. It seemed to work out pretty well as I wrote this up to just remind us which is which. And well, the problem here is we still don't know what the actual value is, so we can only get estimates. But these estimates can be computed through a theorem that we're not going to prove, because in fact, even in a proof-based analysis class, this would be one of the hardest things to do. So for the midpoint rule, the error formula is that the error that we encounter with the midpoint rule is less than or equal than k times b minus a cubed, so length of the interval cubed, divided by 24n squared. Makes a good bit of sense. If your interval is long, then your error is going to be bigger, right? If you use more partitions or more intervals, your error should be smaller. The 24 apparently comes somewhere out of the derivation. The hard part always is, what is this k? Well, the k is the maximum of the second derivative. So it's an upper bound for the absolute value of the, okay, it's the maximum of the absolute value of the second derivative. So it's an upper bound for the absolute value of the second derivative on the interval ab. So apparently somehow the more curvature your function has, the more it resists the approximation, the numerical approximation of its integral with the midpoint rule. We're going to discuss that part a little bit more pictorially, because what we're seeing also here now is for the trapezoidal rule, the numerical error encountered when we do an approximation with the trapezoidal rule is bounded by k times length of the interval cubed divided by 12n squared. Again, that makes sense. If you have a long interval, your error is going to be larger than if you have a short interval. Your estimate is going to be more accurate if you use more subintervals. The k is actually the same k as up here, so it's the maximum of the absolute values of the second derivative. So it's an upper bound for the absolute value of the second derivative on AB. That's what we're going to discuss. It seems to make sense. If a function has a lot of curvature, it's quite a ways away from being a straight line, and with the trapezoidal rule, we approximate with straight lines. We can also see that the error estimate reflects what we've seen empirically, and that is that we're only dividing by 12 in the trapezoidal rule, and that just comes out of the derivation, whereas we're dividing by 24 in the error estimate for the midpoint rule. Everything else is the same, so we can expect the midpoint rule to be about twice as accurate as the trapezoidal rule, which is geometrically interesting because our intuition makes it somehow feel as if the trapezoids approximate the area better than the midpoints. Well, the trapezoids approximate the function better, but the midpoint rule, because those overshoots and undershoots on the left and the right side, or vice versa, those things just cancel so nice that we approximate the area better, which is kind of cool. Simpson's rule is the most exact of them all. The numerical error that is encountered when you do Simpson's rule is bounded by a c, and it's going to be defined similarly here, times b minus a to the fifth. So okay, the longer your interval is, the bigger your error is, and we've got a problem here in that long intervals, you've got a fifth power here, divided by 118 into the fourth. Again, when you have more subintervals, you get a better approximation. But what makes Simpson's rule so good is that whereas here the n goes quadratically in the denominator, as well as here, in Simpson's rule, the n goes in the denominator with a fourth power. So when n equals 10 gives us a division by 100 here and here, it gives us a division by 10,000 here. That's why Simpson's rule is becoming so much more accurate, so much faster than the other two rules. The hard part always is to figure out what this c is, and for Simpson's rule, basically the c is the maximum of the absolute values of the fourth derivative. So it's an upper bound for the absolute value of the fourth derivative on AB. That sort of also makes sense. In the trapezoidal rule, we approximate with line segments. Line segments don't have curvature, so curvature is probably going to introduce error. In Simpson's rule, we approximate with quadratics. Well, quadratics have curvature, so they ought to fit second derivatives rather well. It turns out, intuitively, I would think the third derivative ought to be what tells us what the problem is. But the way things work out, and here again, really, we just have to refer to the derivations. It is a lot deeper in the theory than we would want to go in a calculus class. The fourth derivative derives the error in the Simpson's rule. Okay, so a lot of things are intuitive. Long interval means error is potentially worse. Lots of evaluations means the error is smaller. Midpoint rule is more accurate than trapezoidal rule. Simpson's rule is more accurate than midpoint rule typically. And the value, the k, let's discuss that real quick for the trapezoidal rule. And so let's just take a look at a function f where we approximate the area with a trapezoid. Well, then the trapezoidal rule evaluates the function at xk minus 1 and at xk. And now let's compare that for three different functions f, g, and h. Well, f has a certain amount of curvature, we get a certain error. Let's take a look at a function g that, well, we can just see from what we've done with differential calculus, g has a whole lot less curvature than f, right? And because g has a whole lot less curvature than f, it's a whole lot closer to the trapezoid, and so we should get a smaller error. Whereas this function h here has a whole lot more curvature, a bigger second derivative, than f, and so that means the trapezoids shouldn't be as good an approximation. Okay, so after all that, let's talk about how to work with the error bounds. So now we're really getting back to what we need you to do. There's two ways to work with errors. On one hand, we could work with them a posteriori or after the fact, and that's basically when somebody says, look, I've approximated this integral with this method. How far off is my result? Sometimes you are just given data and you have to figure out how good that data is. A priori, or before the fact, is a design job, basically. That's where you say, okay, I want to estimate this integral with such and such a method. How do I choose my n to be as close as desired to the result? We're going to show an example for either of these two. The first example is that we want to estimate the error encountered when using the trapezoidal rule with 4 intervals to approximate the integral of that function that we had before. So this is still a toy problem, but it's going to show that the error estimate is an upper bound. It's not going to be exact, but it's going to give us a worst case estimate for our error. So how do we do that? Well, we need that ugly k, right? So we need the function, 1 minus x cubed. We need the derivative, which is negative 3x squared. We need the second derivative, which is negative 6x. Typically, you'd want to graph that thing, but if we're looking at this, negative 6x absolute value is 6x, and on the interval from 0 to 1, the largest value that can get is 6. Just take the absolute value is 6x. The largest value is assumed on the right boundary here. That isn't always the case, but here it is. And so that k is 6. And that means with n equals 4, a equals 0, b equals 1, right? All of a sudden this becomes primitive. You can use that error formula as soon as you have k, n, a, and b. And it's just plug in the numbers and see what you get. So we get that the error with that we would make with the trapezoidal rule is bounded by k times b minus a cubed over 12n squared. Well, you plug in the numbers. For goodness sakes, that can't be that bad. 1 minus 0, of course, is 1. 6 over 12 is 1/2, so we end up with 1 over 32, I think. Yep, 1 over 32. That's 0.03125, and if you go back to what the trapezoidal rule actually gives us, and I even say that this is consistent with the actual estimate. I went back and copied that out. The actual estimate was 0.734375, which is off the actual result of 0.75 by less than the above error bound, because it's off by less than 0.03. So the other thing that we have to remember there is that the error bounds just give us upper bounds for the error. They can't give us the exact error, because if we had a way to figure out what the exact error is, we would take our estimate, subtract the exact error, and have an exact result, right? So now let's take a look at an actual example. And so now I want to use Simpson's rule to approximate the integral from -2 to 2 of this function for which we raised the methods, so that the error satisfies that the Simpson's rule error is bounded by 10 to the -3, which would mean that we have roughly 3 accurate digits. Okay, and so here again, by now we know error estimation as long as we have the error formulas, and check with your teacher if you have a formula sheet for these things for a test, because they're a bit ugly to memorize, right? But basically, as soon as we have the error formulas, we find n, we find a, we find b, we plug them in, we find the k, and then it's just getting a number. So the first step here is to find this c, because that's the hard part, right? So we need the function. We need the first derivative. Well, that's just the chain rule, right? The 1 over root 2 pi will drag through everything, and I will say a few things at the end about how we could save ourselves some work in computing this integral also. But right now, let's just take a naive approach and just stay with exactly this function. Okay, so we keep the 1 over root 2 pi all the way through. Derivative of an exponential is the exponential itself times the derivative of what we have in the exponent, and so you just get a -x. Second derivative, if necessary, work it out step by step. What do we have here? We have a product rule, right? So first, we take the derivative of the first, which is 1 over root 2 pi e to the -x squared times -x, and then we have times another -x, so we get an x squared. And then we have derivative of the second, which is -1 times the first. Factoring out the exponential gives us x squared minus 1 back here. You can do the same thing again. And so now we get here the derivative of the exponential gives us a -x times this, so it gives us -x cubed plus x, and then the derivative of this thing is a 2x, which gives us another plus 2x, so plus 3x. And the fourth derivative is that we take the derivative of this, which gives us a factor -x, so we get x to the fourth minus 3x squared, and then the derivative of this thing is another minus 3x squared plus 3, and you've got that worked out. Okay, now this is, let me be perfectly honest here, this is a pattern that I saw for this function just as I prepared these slides. It allowed me to get those derivatives very quickly. Typically doing an error estimate with Simpson's rule is hard, mainly because computing those derivatives takes some time, and if it's legit, if your teacher is okay with it, I would use a computer to figure out that fourth derivative, because in the next step, we're also going to use a computer. Namely, we now need to find the maximum, the absolute maximum of this function. Look, we know how to do this. We've learned it in single variable differential calculus, but basically, you graph the thing, and you realize that on the interval from -2 to 2, the error is assumed right in the maximum is assumed right in the middle. And if you're just looking at the picture, and typically an estimate that isn't too far off isn't going to give us an estimate that is too bad for the error here either. So c equals 1.25 would work. And if the maximum is assumed at an ugly value, I would use an estimate like that. Here, because the maximum apparently and actually really is assumed at the center, whoop, I was pushing the wrong button. The best value actually is c equals 3 over root 2 pi, because if you work that out, at 0 the exponential is 1. 1 minus 6 plus 3, 0 minus 0 plus 3 is 3 over root 2 pi, so the best value is c equals 3 over root 2 pi. Well, once we've got that, now it's easy, right? We find n, And, well, okay, so it's not quite easy because we're using the error bound in a different way. We have that the error is guaranteed to be less than c times b minus a over b minus a to the fifth, 180 n to the fourth. That's just something we get the formula. If we make this upper bound less than 10 to the negative 3, then we end up with an inequality that we can solve, right? I can push the n to the fourth over to the right side. I multiply with n to the fourth. I divide by 10 to the negative 3. And what I end up with is, highlighting doesn't want to work here. What I end up with is an n to the fourth on the right side and a 10 cubed on the left side. And so now n has to be greater or equal than the fourth root of what we have over here, which would be the fourth root of 10 cubed times 3 over root 2 pi, or 1.25 would have worked also here. 4 to the fifth, because the interval has length 4, divided by 180. And it turns out that as you work all that out, okay, the 4 to the fifth makes it big, the 10 to the third makes it big, and especially the 4 to the fifth, of course, is really bad. It gets bumped down a bit by the 180, but this number is still big. But what really is the key to making Simpson's rule work is that no matter what you've got under the root is you take a fourth root here. And so this ends up being approximately 9.084. Well, I can't use 9.084 rectangles, but I need to use an even number, so we always round up, so n equals 10 would do it here. And if I work that out, we do the computation for n equals 10, the delta x is 2 minus negative 2 over 10, right? b minus a over 10, which ends up being 4/10. So independent of what we did in the early examples, no, the delta x is not always 1/4. It can be 2/5. And the xk's are a plus k times delta x, which would be negative 2 plus k times 2/5 now. And so now the Simpson approximation from negative 2 to 2, 1 over root 2 pi e to the negative x squared over 2 with 10 intervals will be delta x times our big old ugly formula. And of course, we stick that into a computer. I just realized that n halves minus 1 would be 4. N halves is 5. I plug in my endpoints that have even numbered indices. So that's where the 2k comes from here. I plug in my endpoints where I've got my odd numbered indices. That's where the 2k minus 1 comes from here. And then I let a computer give me the answer. And it's approximately 0.9544633. We know the error is about 10 to the negative 3, which means the result, really what you would report, is that the result is about 0.954, or actually 0.9544, because the next digit may still carry some validity here. And that's the answer. And now this is the answer that is really nice, because this is an answer where we didn't need to know in advance what the result was. This is now something that guarantees us, without prior knowledge of what the integral is, that it's going to be about 0.94. We haven't used any oracles. We've used only valid estimation methods. And then finally, of course, a numerical analyst would tell us right away that there are ways to get away with less computation, because I could integrate from 0 to 2 and double the result, because after all, this thing is an even function. And we could also factor out the 1 over root 2 pi, because that keeps being repeated in every evaluation of the function and doesn't need to be, because we could have just factored that out. Well, we could have factored that out of some of the summations, but we've got those 4s and those 2s. So basically what happens here is that this is actually a maybe. Yeah, so as I said, this is actually a maybe. Sometimes you can do that, and this is what computer scientists then refer to tuning the algorithm, and you have to distinguish between tuning that works for all functions and tuning that only would work for certain functions. And here, of course, we'd have to factor out the 1 over root 2 pi. Let's see, no, the 1 over root 2 pi, actually, the 1 over root 2 pi comes out all the way. Sorry, I'm as tired as you are right now, because the 1 over root 2 pi can be factored out of all those evaluations of the function, but that would only work for this function in particular, right? But if you have a sufficiently important hard numerical task, you would even go to that point. Okay, and that is it, and there isn't anything more. I think I just forgot to erase my templates here at the end. Yeah, the way I make those slides is that I've got templates for examples and various other things at the end, we're done. Okay, this one was exhausting. This one was hard, and that is because numerical estimates are hard. I mean, there are again quite a few things that we have to deal with. Complicated formulas, as well as dealing with inequalities and the like. What you want to take out of this, and really what can be tested, is can you write down the Simpson rule and evaluate it? Of course you can. It's just work out your delta x, work out your xk's, write down the formula, evaluate the functions. It's not that bad. The other thing then is, can you work with the error bounds? Well, yes you can, because as soon as you've got the c or the k, it's just plugging things in, working out the inequalities. It doesn't take that long. However, now, after all this background that I hope you have enjoyed at least a little bit, after all this background that was also designed to remind you that the integral can always be interpreted as area, after all that, we certainly have deserved a break. I am going to eat lunch. I'm not sure what you're going to do, but maybe stay away from the mathematics for a little bit, and then, of course, get back and do some homework problems. Have fun.